Well, have you ever looked up at the night sky, a velvet canvas sprinkled with countless points of light, and felt a sense of profound wonder? A feeling of connection to something vast, ancient, powerful? I have. Each of those lights, those distant suns, tells a story of unimaginable forces, birth, life, death. They aren't just pretty decorations in our sky. They are the engines of cosmic creation, the crucibles where the very stuff of the universe is forged. And we, you and I, are intimately connected to them. We are, in a very real sense, stardust. So, come with me. Let's embark on a journey, a brief but exhilarating voyage across space and time. We'll peel back the layers of mystery that shroud these celestial behemoths. We'll travel from stellar nurseries where new suns are born to the violent, explosive ends of the most massive stars. We'll learn that what we see with our eyes is just a faint echo of the incredible physics playing out across light years of empty space. This isn't just astronomy, it's our cosmic family history. Imagine a fire so immense, so powerful, it dwarfs anything we could ever create on Earth. Now imagine that fire is not burning wood or gas, but the very fabric of matter itself. This is what a star is, a colossal nuclear fusion reactor suspended in the vacuum of space. Deep within its core, the pressure and temperature are so extreme. We're talking millions of degrees. The fundamental building blocks of the universe are forced together, a cosmic forge of unimaginable intensity. In this stellar heart, hydrogen atoms are squeezed with such relentless force that they overcome their natural repulsion. They fuse. They merge to become a new element, helium. This act of transformation, this alchemical miracle, is not a quiet process. It releases a torrent of energy. That energy is carried as photons, particles of light. This energy is the star's lifeblood, the source of its brilliance and warmth. This outward push of energy fights a constant titanic battle against the inward pull of the star's own immense gravity. The titanic battle, energy outward versus gravity inward. When you look at the stars, you might notice subtle differences in their color. Some appear bluish-white, others a brilliant yellow, and some a deep ruby red. This isn't just a cosmic light show, it's a celestial thermometer. A star's color is a direct indicator of its surface temperature. The hottest stars burn with a dazzling blue or blue-white light. Their color tells a story of their energy, their temperature, and their place in the cosmic hierarchy. The image of a solitary star like our sun, journeying alone through the galaxy, is a powerful one. But it's also a surprisingly rare one. The truth is, most stars have companions. They are not loners but are locked in gravitational embraces with one, two, even more stellar partners. Imagine two massive spheres, two suns, circling each other in an endless waltz. They both orbit a common, invisible point in space between them. This point is called the barycenter, their shared center of mass. The stars can exchange material, with gas flowing from one to the other, dramatically altering their evolution. From a hypothetical planet in one of these systems, you might see two suns in your sky, casting double shadows and creating sunsets of unimaginable beauty. We tend to be impressed by the biggest and the brightest. But the opposite is true. The most common type of star in the Milky Way, by a staggering margin, is the humble red dwarf. The life of a star is a drama of cosmic proportions, an epic story written in gas and gravity over millions or billions of years. It all begins in the cold, dark depths of interstellar space within vast clouds of gas and dust called nebulae. These are stellar nurseries. Here, gravity slowly pulls clumps of matter together. As a clump grows, its core heats up, and a protostar is born, glowing from compression. When the core is hot and dense enough to ignite nuclear fusion, a star is truly born and settles on the main sequence. Our sun is in the main sequence right now, and has been for about 4.6 billion years. But fuel is finite. What happens next depends on the star's mass. For a star like our sun, it will swell into a red giant. Then it will shed outer layers to form a planetary nebula, leaving behind a hot, dense core, a white dwarf, roughly the size of Earth. For much more massive stars, the end is far more spectacular, a cataclysmic supernova explosion, leaving an ultra-dense neutron star, or, if massive enough, a black hole, where not even light can escape. When you gaze upon a star, you are not seeing it as it is right now. You are seeing it as it was in the past. The star Betelgeuse, in the constellation Orion, is about 640 light-years away. The light we see from it tonight began its journey around the year 1380, when Geoffrey Chaucer was writing the Canterbury Tales. The night sky is not a snapshot, it's a history book. Look at your hand. Well, consider the calcium in your bones, the iron in your blood, the carbon that forms the basis of your cells. Where did it all come from? The Big Bang created hydrogen, helium, and a little bit of lithium. But, the heavier elements were not present at the dawn of time. They were created later in the hearts of stars. You are, quite literally, made of stardust. Through a process called stellar nucleosynthesis, stars spend their lives fusing lighter elements into heavier ones. In their cores, they turn hydrogen into helium. As they age and heat up, they begin fusing helium into carbon and oxygen. In the most massive stars, this process continues, creating a layered onion-like structure. Neon, magnesium, silicon, and finally iron are forged in this incredible cosmic pressure cooker. When a massive star, not quite massive enough to form a black hole, explodes in a supernova, its core collapses under its own gravity. Protons and electrons are crushed together, forming neutrons, creating a neutron star. The density is almost beyond comprehension. A single teaspoon of neutron star material would weigh billions of tons on Earth, as much as a mountain. Some neutron stars spin incredibly rapidly, hundreds of times per second. Powerful magnetic fields create beams of radiation from the poles. We call them pulsars, cosmic lighthouses. The death of a massive star is not a quiet affair. It is the most powerful explosion the universe has witnessed since the Big Bang itself. For a few weeks or months, a single supernova can outshine its entire host galaxy. Think about that. It can radiate more energy than hundreds of billions of stars combined. These explosions are not just acts of destruction. They are fundamental to the cosmic ecosystem. They also send powerful shockwaves through space, which can trigger the collapse of nearby gas clouds, initiating new rounds of star formation. The word star conjures a single image, but the reality is a zoo of incredible diversity in size and scale. Consider a star like UY Scuti, one of the largest known stars. If you were to place UY Scuti at the center of our solar system, its surface would extend out past the orbit of Jupiter. It is so vast that a commercial airliner flying at top speed would take over 1,000 years to circle it just once. And so, our brief journey comes to an end. We've traveled from the fusion-powered hearts of stars to their violent, explosive deaths. The elements forged in these distant cosmic furnaces, the carbon, the oxygen, the iron, were scattered across space, eventually coming together to form our planet, our ecosystem, and our very bodies. We are not separate from the universe. We are a way for the universe to know itself. The cosmos is not just out there, it's in us. So the next time you find yourself under a clear, dark sky, look up. The universe is telling the most spectacular story of all, and you are a part of it. The story is written in starlight. All you have to do is read it.